actually pretty easy.
Okay.
The one thing you have to realize is that that is an angle. In fact, it's a fourth quadrant angle. Okay? So for the moment, let's just write. You see why it's got to be a fourth quadrant angle?
Well, it has to be.
It's because the argument on tan is negative. On inverse tan, rather.
And it has to be between negative pi over 2 and pi over 2, right?
No, it's got to be, well, first of all, let's start again. Let's not talk about the quadrant yet. How do we solve this? Well, we can solve it without knowing that angle. I'm just going to make a triangle and start labeling it. Now, what can I label?
You can label opposite and adjacent.
Okay, so the opposite is x, and the adjacent is 1.
Yeah.
Therefore, the tangent of theta would be x over 1, which means we would be taking the inverse tan of x. Now, let's ignore for the moment that there's a negative sign in front of the x. It doesn't really matter. But the fact is, now we can label the third side of this triangle. What's my third side? What is it?
X squared plus 1.
Always it's square root of.
Oh, square, yeah, sorry.
Anytime you're solving a right triangle, your answer starts with square root of. Sometimes it's the square root of a perfect square number, so it turns into a whole number, but it's always square root of. Okay, now what's the cosecant of theta?
So that is not opposite over hypotenuse. So it's third x squared plus 1 over x.
Correct. Now, we need to put a plus or minus sign on this. And that is completely dependent on which quadrant it's in and what this function is in that quadrant. So, you know how I see it's the fourth quadrant?
Yeah, because you were doing the thing with a.
Well, if I did this, if I said the inverse tan of negative 1, that's fourth quadrant. That's minus 45 degrees. If I say the inverse tan of positive 1, that's first quadrant. When you're dealing with inverse tan, your answer is either first quadrant or fourth quadrant. It's not the second or the third. It's always first or fourth. Well, in this case, it's fourth because it's a negative angle. Or it's a negative argument. Excuse me. It's not a negative angle. It's a negative argument, which makes it fourth quadrant. So what is cosecant in the fourth quadrant? Positive or negative?
It's negative.
There's my answer. And notice we never had to figure out what theta was. In other words, even though I said let's make that an angle, it was just so that you would consider it an angle. And it would allow us to draw this picture and dimension it. Then you could figure out what the cosecant of that theta was also. And all of these problems where you have the trig function of an inverse trig function can be done this way, every one of them. You do not have to solve for what this angle is. Now in this particular case we wouldn't have been able to anyway, but sometimes they'll stick numbers in here, not variables, and you could actually solve for the angle, but you don't need to. Now if it's the reverse situation, let's say it was the inverse cosecant of the tangent, that's a different problem altogether. Now that's not an angle. That's a ratio. Where it's the angle is that whole thing is the angle. But the only way to solve it is to work from the inside out, solve for what the tan of that is, and then solve for what the cosecant of that number is. So when they're reversed, it's harder because you actually have to maybe use a calculator or figure out trig functions. But when it's this way, you don't. You can always solve it this way where you do not even solve for theta.
Yeah.
All right, what else you got?
So this next one is with the bracket. Negative secant, that is parentheses, negative 7x plus.
Hold on, I'm having a terrible time understanding you, Max. Say again, starting from the start.
Alright, so far, and then parentheses, negative 7x plus 2 pi.
Plus what?
2 pi.
That it?
Parentheses, minus 11.
All still inside the parentheses?
No, the
Okay.
minus 11.
Yeah, I didn't think that was going to. When I started looking at it, I realized that can't be inside the parentheses.
Yeah.
Minus 11, like that, right?
Yes.
And this is an expression or an equation? Is this all equal to 0? Or do they just want you to evaluate it?
Well, this is the sheet it's on says hand graphing review. So
Oh, she wants you to graph this.
Yeah.
Okay. Well, she wants you to graph it using transformations, right?
Well, usually we lay out like the amplitude, vertical shift, horizontal shift.
Okay, that's all sinusoid. That's all sinusoid stuff. So, first of all, let's figure out what secant of x looks like, because that's the parent function. Secant of x. Okay? Well, secant's the reciprocal of cosine, so it looks something like this. There is one period of the secant of x. Okay? Now, let's deal with all of these transformations. Well, the first thing we have to deal with are the two reflections. Ooh, yeah. No, that's okay. Let's first of all realize that when we graph the secant of x plus 2 pi, it's going to give us the same answer, right? Just like the sine of 30 degrees is the same as the sine of 390. Adding 2 pi doesn't change the value at all. So let's cross that off for the moment and not deal with any kind of shifts like phase shifts. You don't have to treat that as a phase shift. We can just treat the fact that minus 7x is the same angle as minus 7x plus 2 pi. Okay, so let's deal with this negative sign. What's the implications of that negative sign?
Well, so that would flip it, but then the negative in front of the 7 would also flip it.
Let's do it one at a time. Let's do it one at a time.
That's over the x-axis.
The first one's over the x-axis. So the first flip I'm going to draw in red. There's what negative secant x looks like. Okay? Now let's look at the second negative sign. That's a flip over the y.
it back to how it was.
No, I got to flip the whole thing. See, I think that what it does is if I do it in green, if I flip the red, oh yeah, you're right. It doesn't flip it to how it was. It flips it to there and there, which is actually the same secant function. In other words, my green is secant x. It's just two different periods. It's this period, the green at the bottom, and I've shifted it over on the left. But always remember, the secant x goes from negative infinity to infinity. The domain is everywhere. Okay? So the last thing we have to do is what? What's the consequence of the minus 11?
Shift it down 11.
Okay. Since I don't have room to shift it down 11, I'm going to shift the x-axis up 11. Because I know this is at 1 for the start. It's actually at 7. But after we shift everything, we'll be fine. In other words, I know that it's 14 units between the bottom of that and the top of this, right? Because the 7 is a vertical stretch factor. I didn't draw it on there because I don't have room. If I were to draw the blue, in other words, if I want to know what secant of 7x looks like, it basically is something like that. Where that point is 7 minus 7, and that point is plus 7. All right? Now the last thing is to shift it down 11. Well, that means the point that was at 7 is now at minus 4. And the point that was at minus 7 is now at minus 18. And I basically can move my horizontal axis up by 11 points, which is the same as moving everything else down by 11. So there's my x-axis, and the blue represents that function. And in fact, it is now negative secant of negative 7x minus 11. Now, if we go back and stick that 2 pi in there, it doesn't change anything. Our answer is still the blue curve. In other words, if I were to draw a bunch of periods of this in blue, the next one would go there, the next one would go here, the next one would go here, you with me? The next one would go here. In other words, adding 2 pi doesn't do anything inside the parentheses. So I was right to take that out to begin with and graph the whole thing as if it wasn't there. Unless she only wanted you to graph one period of this thing. And if she wanted you to only graph one period, it's probably this one here. Because that's 2 pi to the right of my original blue line. If she wants you to just graph the function, then you can do it the way I did it. Now, let's talk about one last thing that we kind of didn't talk about.
Okay.
When I have this, first of all, the secant of minus x, since secant is the reciprocal of cosine, the secant of minus x is the same as the secant of x. So minus the secant of minus x is the same as minus secant of x. So really, yeah, and that gave us this curve. In other words, when we took minus secant of x, that was just a flip over the x-axis of our secant curve, the black curve. And that's what the blue curve is a flip over the x-axis. It is back here, but it could just as easily be this and this. And when I say that, I hope you know what I mean. In other words, one period is my green, but the whole curve is all of them.
Yeah.
All right. You got another one?
So this one is just, I just have one question.
Okay.
So when we're graphing these for a tan curve,
Uh-huh.
so if it's tan, we can do that by graphing a.
The difference between the tan curve is it has a period of pi, not 2 pi.
Yeah, I know that. And then you do it as a cosine curve, and then where the points back up how that graph and how you get your normal tan.
No, tan curve, you should memorize tan curve. Tan curve looks like that.
Yeah.
Goes from minus pi over 2 to pi over 2. So I guess I'm not sure what you're asking. What function are they wanting you to graph?
Well, no, I don't know. Is cotangent the opposite of that? Like, does it curve the other way?
Yes. And it starts at a different place. Cotan goes from 0 to pi, always decreasing. Where your vertical asymptotes are at 0 and pi, not the same place as they are for tangent. Notice the vertical asymptotes on tangent occur at 90 degrees and minus 90 degrees, whereas on cotangent they occur at 0 and pi.
Yeah.
Now, what is frequently confusing is if a negative tangent curve has the same shape as a cotangent curve. It's just horizontally shifted. Yeah, if I draw a negative tangent curve, it looks like this, right? Well, that looks exactly the same place. It's just this one goes from minus 90 to plus 90. This one goes from 0 to pi. So this one would be the cotangent of x. This one would be the minus tangent of x.
Okay. And then, I think I'm good now. That makes sense.
Okay. Be probably clearer if we had a specific problem we could draw, but I mean, it's very important. When you were talking about the tangent, you mentioned it has something to do with cosine. It doesn't.
Yeah.
Really.
So the way that our teacher taught us how to graph things, for example, like if it was a secant problem,
yeah.
You graph it.
Now I know what you're saying. Now I know what you're saying. Now I know what you're saying. You're saying if you want to graph the cosecant, it goes on tops and bottoms of the sine curve.
Yeah,
So the cosecant curve would be my top u and my bottom u. And the same with the cosine curve and the secant. The secant sits on top of the cosine curve, tops and bottoms. But tangent and cotangent do not. Tangent and cotangent look exactly like I had drawn them. Just like that.
Yeah.
And you just have to memorize it. And don't let me confuse you by drawing this negative tangent. That's the tangent of x right there.
And so, the way that our teacher said you can do it, like, for example, if I have a tangent graph, is to take all the numbers from it and do a cosine graph, and then that gives you the asymptote, so you know where.
Oh, I see what she's saying. Well, no, I see. Okay. Here's what she's saying. Because tangent is equal to sine over cosine, wherever cosine is going to be 0, my tangent curve is going to be undefined. In other words, I've got to have an asymptote right there for the tangent curve. And I got to have another one right here. Well, those points are minus pi over 2 and pi over 2. Because she's right. In other words, whenever cosine of x is 0, well then tangent's going to be undefined. That's where its asymptotes have to be.
Yeah.
And cosine of x is equal to 0 at pi over 2 and minus pi over 2.
Yeah, and then for cotangent we would do it the same way except sine.
Only it's cosine over sine, so it's wherever sine of x is equal to 0 is where your asymptotes are. Yeah, and the same thing with secant and cosecant. In other words, secant cannot be defined where cosine is equal to 0. And cosecant cannot be defined where sine is equal to 0.
Yeah.
All right. What else? We got about 5 minutes. We got maybe time for one?
I guess we could just do a practice problem.
Okay.
So I have negative 3 tan parentheses negative x over 7 parentheses plus 6.
All right. Let's start with this argument that's minus x over 7. Tan is odd. And by that I don't mean it's weird looking. I mean it is odd in that the tan of minus x is minus the tan of positive x. Just like sine. Sine is also odd, meaning the sine of minus x is the same as minus the sine of x. Cosine is even. Cosine of minus x equals cosine x. Completely different. Okay? You with me?
Yeah.
So one thing I can immediately do here is take away that tan or that negative sign and that negative sign. Since the tan of minus x is equal to minus the tan of x, then this whole thing gets a little simpler if I can get rid of all these negative signs. So this becomes the same as the tan, and I'm going to write this as 1/7 x, because then it's easy to see that 1/7 is a horizontal stretch factor.
Yeah.
Okay, so how's this going to graph? First of all, we know that tan of x would graph between these 2 points. Right? So what would the tan of 1/7 x look like? Well, instead of this being minus pi over 2, it's going to be minus 7 pi over 2. Instead of this point being pi over 2, it's going to be 7 pi over 2. Because we have a horizontal stretch. In other words, when the coefficient inside the parentheses is less than 1, it acts as a stretch, not a compression, not a squeeze. Okay? So the tan of 1/7 x would look like this. Look just like the tan of x, only it would be spread out horizontally. Okay? Now, the other two adjustments, the 3 and the 6. Just a second, I'm thinking about this. Yeah. It's hard to see the 3. The 3 is a vertical stretch factor. So if I stretch this vertically out with red, it looks something like this. It just becomes skinnier. Okay?
Yeah, and then the 3 is like second one.
Yeah, and the +6, which we're going to do last in green, well, we only have one point on here that we know we can move up 6, and that's that point there. So let's go up to there. We'll call that 6. And now we'll draw the red graph through that green X. So the red graph will go and look something. The green graph will look something like that. And that's what that function's going to look like. Now, my question was, if I flip the tan, hold on a second here. If I flip the tan over the x-axis, it looks like this. Then if I flip it over the y-axis, looks like that. So the minus tan of minus x is exactly what I said it is, which is the same as the tan of x.
Yeah, they cancel each other out pretty much.
Yeah, they do. I just wanted to make sure my reflections weren't interfering with anything. And they don't.
Yeah.
In other words, both reflections end up getting back to the same graph.
Yeah.
All right, Max. We'll let you go.
Yeah, thank you.
And I will talk to you next time.
Yeah, thanks.
Bye-bye.